There has always been a need to transfer information. The main objective of a data communication system is to transfer information from one place to another. Modern data communications technology can trace its heritage back to the 1800s with the development of the telegraph. Data communications technologies, strategies, and equipment continue to develop for an ever-expanding list of applications, from the common telephone to space exploration. This course will focus on the modern data communication technologies commonly used in utility and industrial power system applications. Let's start by introducing you to some of the basic concepts and terminology used in this area. Within a data communication system, there is a transmitter of information, a receiver of information, and a physical link. The communications link can be simplex, half-duplex, or full-duplex. Within a simplex link, data can only flow in one direction with no possibility for a change in direction. A half-duplex link has the capacity to transmit data in either direction. However, data can only flow in one direction at any time. With a full duplex link, data can flow in either or both directions at the same time. The medium over which the signals travel from one device to the other can be described as either baseband or broadband. The most common example of a broadband medium is the cable used for home cable TV. This cable carries many different channels of information at the same time, whereas a baseband medium carries a single channel of information. It can be said that within a baseband link, the entire bandwidth of the link is used to transmit one bit of data at a time. A bit is an abbreviation for binary digit and is the unit of data within a microprocessor. A bit represents either the digit 1 or 0 in the binary numbering system. A byte is composed of 8 bits. Individual characters in the alphabet are typically encoded in an 8-bit code or byte before transmission across a data link. ASCII is one of the most common coding systems used for this purpose. Another popular way of encoding characters is hexadecimal. Hexadecimal is a numbering system with a base of 16. It uses digits 0 through 9 from the decimal system, in addition to the letters A through F. Let's take a look at how the character A is transmitted through a parallel communication link. This type of link uses 8 separate conductors and a common connected between two devices. Each of these 8 conductors carries an electrical voltage, which represents either the logic 1 or logic 0 bit code. The transmitter first converts the ASCII bit pattern for the letter A into voltage levels. Once the transmitter has converted its bit pattern to voltages, it is common to supply some sort of additional signaling to indicate to the receiver when the data is available to be read. For this purpose, we will add an additional conductor as a 9th line. Once the data ready signal has been sent, the data is transmitted to the receiver. In order for the receiver to correctly interpret the data, both the transmitter and receiver need a standard for voltage-to-bit translation. The standard in our example will be that logic 1 is represented by minus 12 volts DC, and logic 0 is represented by 0 volts DC. It is common practice for the receiver to signal the transmitter that the data has been read. The transmitter will then know it can send the next character. A 10th line will be added for this purpose. These 2 additional conductors form a signaling mechanism between the two devices known as a hardware handshake. Now let's take a look at serial data communication links. With a serial link, only 2 wires are required between the transmitter and receiver. The 8 electrical on-off voltage signals are sent in a sequence on the 2 wires with reference to a time base. With serial communications, the data transfer is done bit by bit. To ensure that the receiver of the data knows what to do with the data bits, the data is usually arranged in a particular format. Some additional information is also added so that the message can be effectively transmitted and understood at the receiving end. Let's take a look at the most common form of serial link, the asynchronous serial data communication link. To better understand how these links function, let's see how data is transmitted across this type of link. An asynchronous system is one where there is no fixed timing relationship for the transfer of data packets. However, once a start bit has started the transmission, the bits of each character are transmitted precisely at a specific bit rate. The receiver's clock is set to start timing from the leading edge of the start bit, and then reads each of the following bits at what it thinks is the center of each bit time and records each bit as either a logic 1 or logic 0. After the data bits and parity bit, which we will cover in the next section, a stop bit is transmitted. The stop bit is often considered to be unnecessary because the receiver has been configured to know how many bits are in a character, and therefore already knows that the character is complete. The intent of a stop bit is to set a definite transition time back to the idle voltage, such that the link is ready for the next start bit. During this time, the transmitter's output is usually set to the logic 1 state. Baud rate is a measure of how fast serial data is moving between devices per second. If only 2 voltages are used to transfer the bits between the devices, the baud rate is identical to the maximum number of bits of information that are transmitted per second. As with a parallel link, in the past, a serial link had additional wires used to establish a connection between 2 devices to provide a hardware handshake. Today, most modern microprocessor-based devices, such as GE multilin relays, support a software handshake, and so these extra signals are not needed. The characters transferred between the 2 devices are usually transmitted one after the other in a short burst referred to as a data packet. Data packets contain an address, data, and error check characters. Rules that govern which characters are the address, data, and error information are called the data packet framing. Errors inevitably occur in the transfer of data due to such things as noise and timing errors. Parity error checking is a very simple form of error detection. Let's look at an example where the user has selected even parity. Because the character A has 2 logic 1 bits, the parity bit will be set to logic 0. When the receiver totals the logic 1 bits and the parity bit, it will get an even number. The receiver then recognizes the character was transmitted correctly. Now let's take an example where electromagnetic noise from a motor starter resulted in one of the logic 0 bits changing to a logic 1 state during transmission. When the receiver totals the logic 1 bits and the parity bit, it gets an odd number. Since our parity was set to even, the receiver recognizes it has an error. The receiver then signals the transmitter to resend the character. This error checking is limited to a detection of a single bit error. In general, this is sufficient for low baud rate serial transmissions. The user can elect to use even or odd parity, or ignore parity altogether. The transfer of bits in a communication system using on-off voltages requires a tightly controlled electrical environment. The data communication environment across the short distances between the components of microprocessor-based devices such as a computer is usually stable, and so parallel communication links, known as buses, are common. For data communication with external devices located some distance away, the environment often has a lot of electrical noise. The electrical properties of the cable and external electrical noise lend a strong advantage to serial communication over parallel, and so serial communication links tend to be the norm. These serial links are referred to as a LAN. LAN is an abbreviation for Local Area Network. Typically, a LAN is all of the components that make up a data communication system, which allows a number of independent devices to communicate directly with each other. This connection is generally over a small geographic area, such as a building. A MAN, or Metropolitan Area Network, is formed when the LANs of a group of buildings in close proximity are interconnected together. A WAN, or Wide Area Network, is formed by the interconnection of LANs over a wide area. A typical example of a WAN in a utility application would be the network that is formed by the interconnection of the substation and control center LANs. The distance between the LANs forming the WAN could be from a few kilometers to hundreds of kilometers. Traditionally, a LAN's topology refers to the physical configuration of the network devices. We say traditionally because some like to use the term logical topology, which refers to the topic of virtual LANs. The LAN topologies supported by GE Multilin's products include point-to-point, bus, star, redundant star, and ring topologies. Networks that are specific to one manufacturer and which work with specific hardware connections and protocols are called closed systems. Usually, these systems and technologies are dated and were developed at a time before standardization or when it was considered unlikely or not desirable to have equipment from other manufacturers included in the network. In many of these dated configurations, a single device acts as a protocol translator that collects data from different devices in the field using a variety of protocols, hence the term protocol translator. The purpose of the data collection is to build up or concentrate the data in one area for storage, monitoring, and control purposes. The data concentrator relays the data back and forth between the field devices, an operator interface, and data storage devices with inherent delays. The term data concentrator refers to a device that performs this function. Open systems are those communication networks that conform to specifications and guidelines which are open to all. This allows equipment from any manufacturer who claims to comply with a particular standard to be used interchangeably on this network. This provides the end users with many choices of equipment suppliers. The network standard being open will tend to be updated on a frequent basis to take advantage of the latest, widely available, and cost-effective hardware and software technologies. The optimal configuration would have all devices directly connected to the LAN, eliminating the need for a relaying device such as a data concentrator and its associated delays. The support of high-speed LAN interfaces is now more common with the increase in power of modern microprocessor-based devices. One of the most important features of a communication system is the need for a common set of rules in order for both the receiver and transmitter to understand each other. This is referred to as the need for compatibility. There are three issues associated with compatibility. The first issue is the pure physical connection standard. The second is the existence of complementary software standards at the transmitter and receiver, which are used in conjunction with the physical standards to make a complete communication system. The third issue is the conformability of the physical connection and software to the Open System Interconnect model, or OSI model. There are 7 worldwide organizations which are involved in drawing up standards or recommendations affecting data communications. When one of these organizations creates a new standard, the name of this organization appears as part of the name of the new standard. Faced with the proliferation of closed network systems, in 1978, the International Standards Organization defined a reference model for communication between open systems, which is called the Open System Interconnection Model. This model is composed of 7 layers. Each layer has a defined purpose and interfaces with the layer above and below it. Let's take a look at the role of each layer. The physical layer includes elements involved with the actual transmission and reception of signals such as physical connections between the device and the network, network topology, electrical aspects of signaling voltages and currents, for example, which voltage levels are considered a logic 1 and logic 0, in addition to how much current the transmitter must be capable of supplying. Signal modulation technique. For example, is it a simple on-off technique or FM or AM, etc.? Mechanical aspects such as the connectors and physical medium to be used. In utility and industrial power system applications, the most commonly used physical layer standards are RS-232, RS-423, RS-485, 10-100 base T, and 10-100 base F Ethernet. We will learn about these standards in depth in the following sections of this course. The data link layer provides the services that allow communication between devices. This includes framing or separation of messages, error detection and correction mechanism, and an addressing mechanism. While the data link is concerned with the direct exchange of frames among devices on a single communications channel, the network layer is responsible for device-to-device data delivery and optimal routing across multiple data links. These underlying layers might result in packets that are delivered out of sequence, missing, corrupted, or delayed due to lower layer communication issues. To address this, the transport layer provides a guaranteed delivery messaging service that ensures the data is error-free and correctly sequenced, allowing process-to-process communications between devices across a network or multiple networks. The session layer provides a mechanism for the establishment of a communication session between applications running within the devices, while the presentation layer ensures the correct translation of data. The application layer provides the facilities or interface to allow the application's protocols or drivers, such as Modbus or DNP, to use the network.